I welcome everyone to this module. In this module, you study about chordal graphs. Chordal and related graphs have been studied extensively in recent years. One important feature is that many NP-hard problems become polynomial when restricted to chordal graphs. The motivation for the term chord is geometric. If a cycle is drawn with its vertices in order on a circle and its chords are drawn as line segments, then the chords of the cycle are the chords of the circle. First, let us see what is meant by chord. Definition of a chord: a chord of a cycle C is an edge not in C whose endpoints lie in C. Now, let's see the definition of the chordal graph. A chordal graph is a simple graph in which every cycle of length at least 4 has a chord. Remark: a cycle is split into two smaller cycles by a chord. In a chordal graph, if at least one of the cycles is not a triangle, then it has another chord, and so on. Finally, every cycle is split into a number of triangles. That is why a chordal graph is also called as a triangulated graph. Example 1, every complete graph is a chordal graph. Example 2, every tree is a chordal graph. We will see some more examples regarding chordal graph. Let's see some examples of chordal graph. I already told you every complete graph is a chordal graph. So here I am having K4, a complete graph on 4 vertices A, B, C, D, and since every vertices are adjacent to each other, this is a complete graph. Okay, so what is the definition of a chordal graph? For a chordal graph, every cycle of length at least 4 should have a chord. So here I am going to consider the cycle A, B, C, D, A, which is of length 4. A, B, C, D, A. This is a cycle of length 4, and here we are having two chords, namely B, D and A, C. So chord of this cycle A, B, C, D, A is B, D and A, C. So cycle of length at least 4 has two chords here, which means that K4 is a chordal graph. Perhaps every complete graph is a chordal graph. This is one such example for that. Next, we will see another example. So here I am having another graph consisting of 5 vertices A, B, C, D, E. So here I am going to consider the cycle of length 4 and cycle of length 5. Here it does not have any cycle of length greater than 5. So it is enough if I consider a cycle of length 4 and the cycle of length 5. So here this is a cycle A, B, C, D, E, A. This is a cycle of length 5. I repeat again, this is A, B, B, C, C, D, D, E and E, A. So in this cycle, how many chords are we having? Here we are having two chords, namely EB and EC. That is, EC and EB are the chords for this cycle. So we consider one such cycle of length 5, and here we are having two chords. There is no other cycle of length 5. So we will move to the cycle of length 4. So this is one such cycle, that is A, B, B, C, C, E, E, A. That is A, B, C, E, A. This is a cycle of length 4. Here we are having one chord called EB. So chord of A, B, C, E, A is EB. This is a cycle of length 4 and the chord is EB. We do have another cycle of length 4, that is E, B, C, D, E. This is also a cycle of length 4. Here we are having a chord called EC. So EC is a chord of the cycle E, B, C, D, E. So we consider all the cycles of length greater than or equal to 4, and all the cycles are known to have chords. Some cycle is having two chords also, which means that it is a chordal graph. Okay. So from the definition itself, we can say a cycle is not a chordal graph. For example, consider this cycle C4. So C4 is a cycle. So, we are having a cycle of length 4 A, B, C, D, A. But what happens here? We cannot find a chord here, which means that we are having a cycle of length 4 but it does not have a chord. So, this is not a chordal graph. Same holds good for all other cycles also. But C4 is the smallest cycle which does not, that is smallest graph which does not have any chord, which means is the smallest graph, that is not a chordal graph. Next, let us see the following proposition which tells about the induced subgraph of a chordal graph. Proposition 1. Every induced subgraph of a chordal graph is chordal. Let us see the proof. We prove this by the method of contradiction. Let G be a chordal graph and suppose that G has an induced subgraph that is not chordal. Then the induced subgraph contains an induced cycle Ck where k greater than or equal to 4. Clearly, Ck is an induced subgraph of the graph G, which is a contradiction to G is chordal. Hence, every induced subgraph of G is chordal. Now, let us see the following note which is very clear from the above proposition. Note, if we delete any vertex from a chordal graph, the resulting graph obtained is again a chordal graph. Now, let us see the definition of a vertex cut. A vertex cut, any set S subset of V of G, that is set of all vertices, in a connected graph G, which after deletion from G leaves a disconnected graph, is called a separator or vertex cut. Now, let us see the definition of a click cut. A click cut is a vertex cut which is also a click. Now, let us see the following theorem. Theorem 1, the statement is, let G be a connected chordal graph which is not complete. If S is a minimal vertex cut of G, then S is a click cut of G. We shall see the proof now. Let G be a connected chordal graph which is not complete. So, we assume that let S be a minimal vertex cut of G. So, we are going to prove S is a click cut of G. Suppose that S is not a click cut of G, then S contains two non-adjacent vertices, say X and Y. Let G1 and G2 be two components of G minus S. Since S is a minimal cut, the vertices X and Y are joined to the vertices in both G1 and G2. Let Pi be a shortest XY path, all of whose internal vertices lie in Gi, where I ranges from 1, 2. Then P1 union P2 is an induced cycle of length at least 4, which is a contradiction. Hence, S is a click cut of G. From theorem 1, one may deduce that every connected chordal graph can be built by pasting together complete graphs in a tree-like fashion. Now, let us see the following remark. Consider the chordal graph G1 and G2 as shown on the screen. For the subset S1 is equal to set consisting of U1, V1, X1 of V of G1 and the subset S2 consisting of U2, W2, X2 of V of G2. Let the graph G3, actually we are going to construct G3 obtained by identifying the vertices in the complete subgraph G1 of S1, that is the induced subgraph of G1 with the vertices S1, with the vertices in the complete subgraph G2 of S2, where U1 and U2 are identified, V1 and X2 are identified, X1 and W2 are identified. Then the graph G3 shown in the figure on the screen is also a chordal graph. Let us see the following definition of S branches. Let S be a minimum vertex cut of a non-complete connected graph G, and let G1, G2, etc. Gk, where k greater than or equal to 2 be the components of G minus S. So, S is a vertex cut, so obviously we are having components, we are taking the components as Gi's. Then the subgraphs Bi is equal to G of V of Gi's union S are called the branches of G at S or the S branches of G. Let's see the following theorem. This is theorem 2 and the statement is, let G be a graph obtained by identifying two complete subgraphs of the same order in two graphs G1 and G2. Then G is chordal if and only if G1 and G2 are chordal. We shall see the proof now. Let G1 and G2 be two graphs containing complete subgraphs H1 and H2 respectively of the same order, and G be the graphs obtained by identifying the vertices of H1 with the vertices of H2 in a one-on-one manner. We proved this by the method of contradiction as we did in the above theorem, previous theorem. Suppose that G is not chordal, then G contains a cycle of length 4 or more having no chord, which follows that C must belong to G1 or G2. This we prove used by the definition of chordal graph. That is, if G is not chordal, then either G1 or G2 is not chordal. Conversely, with all a generality, we are going to assume G1 is not chordal. Then G1 contains a cycle C of length 4 or more having no chords, which follows that C must belong to G. That is, if either G1 or G2 is not chordal, then G is also not chordal. Thus, G is chordal if and only if G1 and G2 are chordal. Hence, we proved the theorem, and we note that the conditions given in the above theorem are not only sufficient conditions for a graph to be chordal, but they are necessary as well. Next, let's see the following theorem. This is theorem 3. The statement is, a graph G is chordal if and only if G can be obtained by identifying two complete subgraphs of the same order in two chordal graphs. We shall see the proof now. For proving this, it is enough to prove that every chordal graph can be obtained from two chordal graphs by identifying two complete graphs of the same order in these two graphs. If G is complete, let me say that is Kn, then G is chordal. Since every complete graph is a chordal graph and can trivially be obtained by identifying the vertices of G1, that is equal to Kn, and the vertices of G2, that is also equal to Kn in any one-on-one manner. Hence, assume that G is a connected chordal graph that is not complete. Let S be a minimum vertex cut of G. Now, let V1 be the vertex set of one component of G minus S, and V2 is equal to V of G minus V1 union S. Consider the two S branches. G1 is equal to G of V1 union S and G2 is equal to G of V2 union S of G. These are two S branches. Consequently, G is obtained by identifying the vertices of S in G1 and G2. We now show that G of S is complete. Suppose cardinality of S is equal to 1, then G of S is complete. Hence, we may assume that cardinality of S greater than or equal to 2. Then, each vertex V in S is adjacent to at least one vertex in each component of G minus S. For otherwise, S minus singleton V is a vertex cut of G, that is impossible. Let U, W belong to S. Hence, there are UW paths in G1 where every vertex except U and W belongs to V1. Among all such paths, let P is equal to U, x1, x2, etc. xs, W be a path of minimum length. Similarly, let P dash is equal to U, y1, y2, etc. yt, W be a UW path of minimum length where every vertex except U and W belongs to V2. Hence, the cycle C U x1, x2, xs, W, y1, yt, yt minus 1, y1 U is a cycle of length 4 or more in G. Since G is chordal, C contains a chord. Since S is a vertex cut of G, no vertex xi 1 less than or equal to I less than or equal to S can be adjacent to a vertex yj 1 less than or equal to j less than or equal to t. Furthermore, no non-consecutive vertices of P or P dash can be adjacent due to the manner in which P and P dash are defined. Thus, UW belong to E of G, which implies that G of S is complete. By above theorem, G1 and G2 are chordal. Let us see the definition of S component. Definition: let G be a connected graph which is not complete. Let S be a vertex cut of G, and let X be the vertex set of a component of G minus S. Then the subgraph H of G induced by X union S is called an S component of G. We shall see a theorem now. Theorem 4, the statement goes like this: let G be a connected chordal graph and let V1 be a maximal clique of G. Then the maximal cliques of G can be arranged in a sequence V1, V2, etc. Vk such that Vj intersection with union I minus 1 to j minus 1 Vi is a clique of G where j lies between 2 and k. We shall see the proof now. Suppose that G is complete, then there is nothing to prove. So, we are going to assume G is not complete and let S be a minimal vertex cut in G. So, by the theorem 1, S is a clique of G. Let Hi 1 less than or equal to I less than or equal to P be the S components of G, and let Yi be a maximal clique of Hi containing S where I lies between 1 and P. Then the maximal cliques of H1, H2, etc. Hp are also maximal cliques of G, and that every maximal clique of G is a maximal clique of some Hi. With all a generality, suppose that V1 is a maximal clique of H1. By induction, the maximal cliques of H1 can be arranged in a sequence starting with V1 and having the stator property. Likewise, for 2 less than or equal to I less than or equal to P, the maximal cliques of Hi can be arranged in a suitable sequence starting with Yi. The concatenation of these sequences is a sequence of the maximal cliques of G satisfying the stated property. Now, let us see the definition of simplical vertex. A simplical vertex of a graph G is a vertex whose neighbors induce a clique in G. That is, the neighbors are pairwise adjacent in G. Now, let us see an example for simplical vertices. Consider the graph which is on the screen. Okay. So, in this graph, the simplical vertices are S, V and Y, because if we consider V, the neighboring vertices are W and U. W and U are adjacent to each other. So, the neighboring vertices of V are adjacent to each other, then we call V as a simplical vertex. Similarly, for Y, the vertices, that is neighboring vertices, are adjacent with each other, and for S also, the neighboring vertices, that is R and T, are adjacent to each other. So, we call S, V, Y as simplical vertices. Whereas, consider W, the neighboring vertices X and V are not adjacent to each other, which means that W is not a simplical vertex. We shall see the theorem 5. The statement is: a connected chordal graph is either a clique or it contains two non-adjacent simplical vertices. As a prelude, we shall prove the following lemma. Lemma 1: in a chordal graph, for every vertex x, there is a simplicity vertex of G among the vertices farthest from X in G. We shall see the proof now. We are going to prove this lemma by induction on n. Assume for n is equal to 1. Obviously, the one vertex of K1 is simplicity. Assume n is equal to 2. Suppose this is case 1. Suppose X is adjacent to all other vertices. Consider the graph G difference X, G minus X. Since G is a chordal graph, G minus X is also chordal. Now, we apply the induction hypothesis to G difference X. Each simplicity vertex Y of G minus X is also simplicity in G. Since X is adjacent to all of n of U union singleton set Y. N of U is the neighborhood of U. Case 2. Suppose X is not adjacent to all other vertices. Let T be the set of vertices in G with maximum distance from X. Let H be a component of G of T. Let S be the set of vertices in G difference T having neighbors in V of H, and let Q be the component of G difference S containing X. See the figure which is on the screen. We are going to prove S is a clique. Each vertex of S has a neighbor in V of H and a neighbor in Q. Consider two distinct vertices U, V in S. The shortest UV paths through H and through Q is a cycle of length at least 4. This cycle has no chord other than UV, since there are no edges from V of H to V of Q. Since G is chordal, U, V are adjacent to each other. Since U, V is in S were chosen arbitrarily, S is a clique. Now, let G dash is equal to G of S union V of H. This does not contain X and hence is smaller than G. Hence, we apply the induction hypothesis to G dash and a vertex U in S. Since S is a clique, S difference singleton U is a subset of N of U. Whether G dash is a clique or not, it thus has a simplicity vertex Z within V of H. Since the vertex Z is also simplicity in G and Z is a vertex with maximum distance from X as desired, the lemma holds. Now, let us see the definition of perfect elimination ordering. We shall see the definition now. For that, a simplicity order of a graph G is an enumeration V1, V2, etc. Vn of its vertices such that Vi is a simplicity vertex of G of V1, Vi plus 1, etc. Vn, where I lies between 1 and n. These orderings are also called perfect elimination orderings. Now, let us see an example of perfect elimination order. Example 5. Consider the figure which is on the screen now. The above graph has a perfect elimination ordering witnessed by the ordering V2, V1, V3, V4 of its vertices. The following theorem is a characterization of chordal graph. That is the theorem we are going to see now. This theorem. This is theorem 6. A graph G is chordal if and only if it has a perfect elimination ordering. We shall see the proof now. Suppose that G is a graph with perfect elimination ordering. We are going to prove G is a chordal graph. Suppose G is not a chordal graph, then G has a chordless cycle V1, V2, etc. Vi of length L, where L is greater than or equal to 4 in G. Let Vi be the vertex in the cycle that occurs first in the perfect elimination ordering. then Vi minus 1 and Vi plus 1 are neighbors of Vi in G that occur later in the ordering. Since the ordering is perfect, there must be an edge between Vi minus 1 and Vi plus 1, which is a contradiction to the assumption that the cycle is chordless. Hence, G is a chordal graph. Conversely, suppose that G is a chordal graph. We are assuming G is a chordal graph. Then, by the lemma 1, that is lemma we proved now, G has a simplical vertex. Since every induced subgraph of a chordal graph is chordal, this yields a simplical elimination ordering by induction on n. So, we prove the theorem. Now, let us see an algorithm to find a perfect elimination ordering. So, this is an algorithm to find a perfect elimination order. For I is equal to n to 1, let Gi be the graph induced by the vertices Vi plus 1, Vi plus 2, etc. Vn. Test whether Gi has a simplical vertex V. If no, then stop. Gi and therefore G has no perfect elimination order. Else, set Vi is equal to V. V1, etc. Vn is a perfect elimination order. Now, we are in the end of the module. So, in this module, we have seen about chordal graphs and simplical vertex and related examples, and through simplical vertex, we have seen the characterization of a chordal graph and perfect elimination order and an algorithm to find a perfect elimination order and the related theorems also. I hope this module will be so useful to you in the future. If you want to try more examples, you can try, which is given in the script. And thank you. We'll meet once again in the next module. Thank you so much.